Then, you know, okay. So, yeah, I think it is. So we get back to the state. I finished the 300. I finished the 300 right there. Went all the way down, and I didn't make a list of it. You know, bet I did, but bet hit me for it. I know I took a picture of it, and I know you don't really care. I'm going to show it to you here because I was all in trouble. Don't have to show you my email. There you go. All of those are the prime numbers from one agreement. Oh, so satisfying. And yet, you have a list. You know, so, but you need to practice. What's the first number you cross off? Not the first one you start with, you got to cross off something first. What? One. And then the first prime number is a two. And then you cross off the who's. What? All the numbers that two goes into, all the even numbers that two would divide evenly. Because a number, according to the fundamental property of arithmetic, a number is either prime or it's not prime. It's composite. So it either is only divisible by one and itself, or it's a product of primes. So if two is prime, any number that is a product of two is not. So if I'm trying to use a sieve and sift out all the non-primes, cross off all the non-primes, I'm going to cross off all the products of two, all the multiples of two. So that means anything in this column, they're all going to be multiples of two. And it ends in an even number. It would be a short. Multiples of four are basically in the same category. These would all be even. Because you'd be counting every two numbers. Now I'm only going to 140, so. So we're stopping at 140. So we've crossed off all the multiples of two. So the next number that's not crossed off in the sieve is your next prime number, and that's the threes. So three is prime. So all the next non-primes would be multiples of three. Now, some have already been crossed off because they're multiples of three times two. So half of them are going to stop. So 3 times 2 is 6, 3 times 2 is 9, 12, 15, 18, 21, 24, 27. Basically, 3 times an odd number because we already crossed off 3 times 2, 3 times even. So 3 times an odd number is 3 times 9, 3 times 11, 3 times 13, 3 times 14, 3 times 15, 3 times 16, 3 times 17, 51, 18 is 54, 19 is 57, 21 is 63, 22 is 66, 69, 23, 24, 27, 8, 1, 7, 8, 1, 2, 5, 8, 100, 1, 6, 5, 1, 5, 8. Right. What's the divisibility rule, Reed? Yeah, some of the digits is divisible by 3, we can divide by 3. So as I'm doing this, I'm going, really? That's one of them? Just making sure in my head that I was counting. Something like 132. 1 plus 3 is 4. 4 plus 2 is 6. Okay. 3 goes into 6, so 3 goes into that number. Just a fixation on where I'm at. It's like checking your GPS. Are you in the right place? So the next one would be the 5s. So along comes Schoolhouse Rock, which helps you figure it out. 5, 10, 15, 20, 25. All those are going to be crossed off. Because those are multiples of 10. So those are the ones that end in 0. So technically, 5, 15, 25, 35, 45, 45, 45. Those are icons. 6 is nothing. 7. So 7 times the odd, 7 times 3 is already done. 21. 7 times 4, that's even. 7 times 5, already crossed off multiple of 5. 7 times 6 is even. 7 times 7 is 49. 8 is even. 7 times 9 is 63. But 63 is a multiple of 3. If 9 is a multiple. 7 times 10 is even. 7 times 11. 12 is an even. 7 times 13. 91. 7 times 13, 14 even. 7 times 15. 15 is a multiple of 3. So it's not going to work. 7 times 16 is even. 7 times 17. So that would be a 49 and a 70. That's a 119. 18 is even. 7 times 19 would be a 63 and a 70. So 63 and 70 would be 133. And then if you add 7 more, we'd be at 140. And if I check the divisibility rule just in case for 133, just in case, you take this digit, 3, and you multiply by 2, and we get 6. Then you subtract 6 from 13. If this is divisible by 7, 133 is divisible by 7. And it is. I don't know why it was always just told that don't worry about stuff. Don't do it. That's not a really hard thing to do. But if you don't practice it, you won't know. So the next one is 11. So we've already done 11 times 2, 11 times 3, 11 times 5, 11 times 7. We've done all of those. What we haven't done is, let's see. Here's the 11. 22, 32, 24, 55, 66, 77, 88, 99, 110. That's 11 times 10. And then 11 times 11. Don't forget about that. 11 times 11. 11 times another prime number. 11 times 12 would be 132. And then the next one would not be. It's bigger than 130. And times 13. And we've already done 13 times all of those. We've already done 13 times 11. Okay. And 13 times 11 doesn't even fit. So let's see if we can figure this out. 13, 26, 26, then 39, 39. Then we go to 1, that's 13 times 4 is 52. 13 times 5 is 65. 13 times 6 is 78. 13 times 7 is 91. 13 times 8 would be 104. 13 times 9 is going to be 117. 13 times 10 is 130. And then 13 times 11 is going to be 143. And that's it. I think we're done with it because there are no multiples of 13 left to circle. 17. 34 is done. The next one would be, so that's 2. 3 would be, we've already crossed off multiple of 3. We've already crossed off multiple of 5. 7 times 17, crossed off. 9 times 17, or sorry, not 9. 11 times 17, well, we need to be there. 13 times 17 times be there. So we have crossed off any potential composite number. Everything left was prime. 23. Sorry, you stuck on the 19. And 9. 31. 37. 31. 2. 7. 53. 59. 7. 1. So you have 150, 140 numbers in this sieve, in this bowl, and you're shaking it about, and you want to be left with only prime number. So as you shake it about, all the composite numbers have been eliminated, and so we're left with primes only. So the question is, why do we think it works? Why does this work? Remember, this Eratosthenes came up with this 300 BC, 400 years ago. This is number theory. This is part of mathematics, the history of mathematics that it's still relevant today. We still search for larger and larger prime numbers that are billions of digits long. I mean, this is just a 3-digit prime number, 127. Think about a prime number that is 1,000,000 digits long. And you have to see, is it divisible by anything else? And that's where they used to do supercomputers and see if it can calculate, is that a prime number? Why do you think it works? Here's the hint. The fundamental property of Sure, I'm gonna make sure I'm saying, like, stuck between two words. Their own property, blah, 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 blah. We talked about it. Fundamental theorem of arithmetic. Fundamental theorem of arithmetic states every counting number greater than or equal to 2 is either prime or can be factored into a product of prime in a unique way. So in other words, it's either prime or composite. Look at his head. That head is, why do we think of it? Why does that sieve feel us the problems? It says the fundamental theorem of arithmetic. Every single counting number greater than 2 or greater than 2, zero prime or a product or a product. A product. What number do we start with? 2. And it was prime. So that satisfies the first part of the fundamental theorem. What did we cross off that theorem? So we crossed up all the numbers that were products of 2. So we were left with the only number that was a 2. Then we went to the next number that was prime, 3. So we know 3 is prime, but it wasn't crossed off. And then we crossed off all the products of 3. So a number is either prime or it's a product of prime. So the sieve of Aristotle's is sifting through the numbers that are prime and basically getting rid of all the numbers that are products of that prime number. That's why we're left with just a set of prime numbers. Okay. But here comes the quiz. For the most part, it wasn't bad, except for question 2. So we're going to go over question 2. So listen. Half the arts. Understand the results of the Sven, the Christian Denise and Victor. All right. And all the factors of 288. So most part that was pretty good. Some of you didn't arrange it, did not organize it well enough, so you missed a few of the factors. We wanted all the numbers to divide 288 evenly. So 1 times 288, and then with 2 times 100.4, and then 3 times, we think that's going to be 96, and then 4 times 72, and 5 doesn't work, and then 6 times, and we're going to go 6 times 48. And then 7 doesn't work, and then we go 8 times 36. And then 9 is going to work because take out another 3. We're going to get 9 times 32. And then 9 times 10 doesn't work, 11 doesn't work. 12 times, take out a 3 here, that makes it 12. 12 times 3, we're going to get a 24. All right. 13, no, 14, no, 15, no, 16. 16, can I take out a 4? Yes, I can. That is 16 times, take out a 4. I'm going to get a 18. So the next one that I will get to here would be an 18. I'd end up with 18 times 16. But again, I started organized with what 1 times what? 2 times what? There's 3 work. 3 times 96. There's 4 work. And then 5, no. There's 6 work. And then 7, no. And then go to 8. Go to 9. Eventually, you're going to get to 2 numbers that are going to all be almost be close enough to each other that the next one would be the mirror image of any stone. Now, this one, the concept of leap years, let's take that out of the picture. So the blank something occurred in 2024. The last one occurred in 2020. So how many of these things are going to occur in the next 100 years? Do we count 2021? We're in 2026. So in the next 100 years, the last time it happened was 2024. So do we count 2020? We're ready to go from the next 100 years from now. Yes or no? No. Because we're starting in 2026 and we want to go 100 years from now. So basically, we're looking at from 2026 all the way to 2126, the next 100 years. Okay? Now, the last leap year was in 2024. That's the last time we had one of these things happen. They happen every 4 years. So when will, in our little window of opportunity, from 2026 to 2122, when will the next leap year happen? In this week, 2028. Because 4 years from the last one, that will be the next one. That'll be the next leap year that we're going to have. That'll be the next time we have a February 29th. One of my good friends got married on February 29th in about, I think it was 1992. So, 96. Okay. The year 2000 was not a leap year because it ends in 20. So 96, 2004, 2008, 2012, 2016, 2020, 2024. Got married in 92, but he's only been married 7 years. Because February 29th has only happened 7 times. He's only had it celebrate members. That was really smart. So 2028, and then 4 years later, 2032, 2036, 2040, and so on. All the way up to 2000, Now, look at all these numbers. What do they have in common? You see, if it's a leap year, it's divisible by 4. Because they're going up by 4, that's divisible by 4, divisible by 4. So is that one going to be a leap year? No, the 26 is not divisible by 4. So when's the last leap year going to be in our little window of opportunity? 2124. That's going to be the last one. Only 2124. So here's the question. In the next 100 years, leap years occur every 4 years. So between here and here, 100 years, and you get a leap year every 4 years. What's the most leap years you could get? Ignoring the rest of that question, what's the most of these you can get? 100 years. They happen every 4 years. How many possible? What's the most you can chop it into? If you had 100 of anything, and you're going to slice it up into 4 pieces, or pieces of 4 at a time, what's the most number of little four little pieces? 25. You could slice it up into increments of 25, except right here in someplace 2100, no leap year. So the most leap years is 25 in 100 years. And then you subtract 2,100, or there's only 24 leap years. Some people wrote them out. Some people got a little messed up when they went to like 2016 instead of 2000. I don't know, somewhere like 82. Instead of putting 80, they put 82. They messed up in one of their increments of 4, so they miscounted. Some people stopped short. They didn't go all the way to 2,124. It's like, see, you know what? Okay, that's what's what. Right. Let's go on back at 12 o'clock.